Reflection. Metadata is data that describes types and other compiled entities. Some of the important things that metadata describes are types contained in a given assembly, method and field information for a given type, assembly version and identity information, and the other assemblies that a given assembly references. Now, reflection gives us the ability to query this data. So at runtime, we can get knowledge about the actual code that was written rather than just having context with the objects that are created at runtime. We can actually look at the types and the methods that those types contain. It's a very powerful tool, especially if at design time you do not necessarily know about all of the objects which you'll be accessing. So the benefits of metadata are numerous, but here are several that you've probably encountered already. First of all, the CLR uses metadata to link method calls and data references at runtime. So without this metadata, the compiler wouldn't really be able to associate calls to the actual methods that are being accessed. So the CLR uses metadata to carry out verification of code correctness at runtime. Again, because the metadata contains information about the types and the methods within those types, the CLR can make sure that any calls being made to those objects are actually valid. The CLR uses metadata in its implementation of security. It also uses metadata in its implementation of remoting. Now, this remoting is not just with the older remoting technologies. It's also with web services, WCF, anything that requires objects to be passed across an app domain. The CLR uses metadata to define how data is marshaled when using interop. Now, that particular topic we will cover in the final lesson. However, this is also critical because without this ability, we would have to have separate like IDL files that we would need with C++, for instance. So we don't need to have these descriptive language files in addition to our objects and assemblies. The IDE uses metadata to provide IntelliSense. That's a big one. Without IntelliSense, it would be a much different environment when writing your code. It would be more like writing a notepad than it is using Visual Studio. And all .NET assemblies are self-describing through the metadata. As I mentioned, we don't need those separate IDL or .h files to look at what the contents of the code in the assemblies are. We can use reflection to do the interrogation. Reflection is the process of accessing metadata from your application. .NET provides programmatic access to metadata via the types in the system.reflection namespace. In addition to that, we also have the actual type class, which is defined at the system level. Reflection also enables your application to add information to the metadata using attributes. So anytime you add an attribute to your code, such as any of the assembly attributes where you identify like the company name or the assembly version number, or if you add the serializable tag or the flags attribute to an enum, basically that's all using reflection. Dynamic or late binding is also enabled by reflection, that being the ability to not add a reference at compile time, yet load an assembly at runtime for consumption. Then finally, the system.reflection.emit namespace actually allows you to build code dynamically at runtime. So you can actually create code on the fly. Now that's a little advanced for this particular course, but there are many examples of it that you can find online. If you were to look at the reflection.emit namespace and do a search in code project, you will find several examples where people allow you to put C# or VB code in a text box and it'll generate that code on the fly. So what is reflection good for? So most of the time, you're not even aware of the fact that reflection exists. The few times that you've used it up until this point are things like putting attributes on your objects. Now, you implicitly use the metadata when building and loading your application, but no explicit action is required. Okay, because the CLR is looking for all of the assemblies that your application is going to use, and it uses reflection to do this. Then it finds all of those references and loads the appropriate assembly information basically out of the assembly's manifest, so it knows what types are available. The runtime also makes use of metadata under the covers, so you don't actually have to see any of this work being done. The only reason you know it's happening is if you looked at the output window when you're in debug mode, and it'll show you that given assemblies are being loaded into memory. The IDE makes use of the metadata under the covers as well. Now, anytime you hit the dot key after an object name, you get a list of all of the methods that and properties that particular object contains. Now that is all being done via the reflection and metadata that was contained within that particular class definition. So you may encounter a situation where you want to access types without knowing in advance what those types are, and that again is called dynamic binding. Script engines are a classic case where dynamic binding is useful. An example of this would be if you provide in your application an interface that third-party developers can implement, and then when they're done implementing the interfaces, creating their class objects, they would put these in a DLL, and this DLL would then be put maybe in a plugin directory of your application. Then at runtime, your application could look at that directory that contains those DLLs and load each of them individually. Now obviously that could be a security risk, and we're not talking about doing this necessarily in a commercial level, but if you had a framework where you simply had an application where the app is basically a mainframe or an empty page, and then each of the individual parts of the program or each module is maybe a tab on that big empty page. So if you had 5 DLLs loaded in this directory, you might have 5 tabs, each one doing a different portion of your application. Then you could actually dynamically load these at runtime, and since they all implement the same interface, you could then just use reflection to make sure that those interfaces have been implemented and then execute the methods appropriate. This is actually a very common way of handling an extensible framework when you have a large application. Let's take a look at the type class. This is something you've probably used before by either using the type of command or get type, basically any of the functions that will return a type object. So this is the basic root of the reflection API. Now, a lot of people would say, no, assembly is the root. That is correct. However, most of the time you're not interested at objects at the assembly level. You're looking at things at the type level. You want to get to the meat of the assembly. What are the classes? What are the enums and structs? So type is typically the entry point where you'll start doing your reflection. Every instance of a type has a reference to a system.type object specific to that type. So in this case, we have a class called foo, and we would create 2 of them, A and B. And notice here, foo A and foo B both will point to the same type value because they're both of type foo. There are 3 basic methods for accessing system.type. There are actually more than that, however, these are the 3 most common. So we can use the getType method of every object because object provides the getType method and everything derives from object, therefore everything has getType. This will return an object of type type. So as you can see, we have foo a equals new foo, and then we'll say type t is equal to a.getType. Now t will contain a type reference. You can also use type.getType, which is a static method of the type class, provide it a string of the type you wish to find. In this case, we're not going to be able to use the C# alias int. As you can see here, we have to say system.int32. It must be the fully qualified type name. So it's going to be namespace.className or struct or enum. The third way is to use the type of and then the class that you wish to get the type of from. So this is another way to do it without creating an instance of an object, just like the previous one. So we can say type of string in this case. And notice here we can use the C# alias names for the variable types. And this can be any type that you have access to via your using clauses and references. So if you have a running instance of an object, you would use the first method where you'd say that object name dot get type. If you do not have a running instance of an object, and as a matter of fact you don't have a direct reference to the object, in other words it's not in a using clause, etc., you can use the string version type.getType. And then finally, if you have access to the objects themselves or the classes using clauses, etc., then you can use the type of command. So either of these methods will work to return a valid type object. This slide basically shows you what you already know. It's defining what each of these elements in the code sample on the right are. So notice here we have the serializable attribute. Well, yes, that's an attribute. Then we have a class called person, which represents a type. Then within that type we have an event called changed. Then we have several fields. We have M first name and M last name. Then we have properties. In this case, we have first name and last name properties. Then, in our constructor called person, we have parameters. And this would apply to any function that accepted values. So in this case, we have two parameters, last name and first name. And then finally, we have a method, which we're calling toString. So these are the basic object types that are in your code already. And one thing that's interesting is most of these will have a corresponding like event info, field info, or property info class, which will then represent one of these constructs. So let's take a look at the reflection object model. Remember I mentioned before that type is typically the entry point to the reflection object model. However, we can also go up a level by looking at the assembly. Now the assembly represents the unit of distribution as a whole. So if you have a DLL or an executable, that would represent your assembly. Now we don't deal with multi-module assemblies very much in programming. However, if you had multiple modules, you could actually get the individual modules from the assembly object itself. However, since we don't really deal with multiple modules, we can just bypass that and get types directly from the assembly. Just be aware that both the module object and an assembly object contain a getType or getTypes methods, depending if you know which type you're going to get or if you want to get a series of types based off of a similar name. Now, because we know that types can be contained within types, in other words, you can put an enum or another class within a class definition, a type will also have a getNestedType or getNestedTypes method as well. That allows you to look at all the nested types within a given type. Now, once we're at the type level, we have several methods we can execute. And again, these all come in singular and plural. We have getConstructor, getField, getMethod, getProperty, and getEvent. Each one of those will return an info object. So it will either get a constructor info, a field info, method info, property info, or event info object respectively. Also note, in the constructor info object or the method info object, we have the ability to get parameters, which returns, as you probably guessed, parameter info objects. In this example, I'm using reflection to interrogate a set of classes within a given assembly. In this case, I want to get the currently executing assembly, so I will call the getExecutingAssembly static method on the assembly class. That will give me a reference to the assembly that is currently executing, so it's the parent executable in this case. I output the assembly's full name, and as you can see on the right, the name of the assembly is called reflection test. Also notice it has a version, a culture, and a public key token. That refers to the full name of the assembly, and when we talk about strong naming and adding elements or objects to the global assembly cache, we will cover that again. From the assembly, I call getTypes. This will give me a list of all of the types contained within this particular assembly. I have a program class and I have a person class. Those are the two different types I have. If I also had enums at the level of the same level as program or person, that would show up here in the list as well, because an enum is also considered a type along with a struct. Then I take each individual type in turn, and I get the constructors, the events, the fields, the properties, and methods by calling the appropriate get method and getting a constructor info, event info, field info, and property info, and method info object at each step of the way. So you can see on the right hand side in the output what each of those looks like. Pay attention to the add changed method, where we have the system.eventHandler tick1. Now that tick1, just so you know, is the nomenclature that is given by the compiler for generic types. That way you cannot create a type that would interfere with these auto-generated type names, because the tick character, which would be under the tilde, is not valid for standard names in C#. But the compiler is allowed to use whatever naming conventions it likes. Binding flags is an enum that allows you to define how you want to search for specific items when you're using these get methods. Typically, you'll have something like bindingflags.public or bindingflags.static. Now, since we know this is an enum and you see this OR character, that typically means this is going to be a flags enum where you can have overlaid bits, and in fact that is the case. You can also use it with invoke and invoke member and create instance to indicate different behaviors as well. Here are some of the binding flag values. Ignore case is useful if you are searching for a given function or property and you're not sure how the spelling is. So if you're not sure if it's all capital letters or proper case, mixed case, etc., you can use ignore case, so it'll find anything that matches that text pattern regardless of character casing. Instance will make sure that any values that come back from the get methods are instance members. And as you can imagine, we have a static enum value as well to get static members. Then we have public and non-public. Those two binding flags are used to return either publicly accessible members or those members that are not publicly accessible, including private and internal, etc. Then we have change type and operation type binding flags as well, where we have the change type for exact binding indicates that the types of the supplied arguments must exactly match the types of the corresponding formal parameters. So when we are looking for a given method, we can specify we're looking for the overload that contains exactly these types of parameters. That means we don't have to worry about which in this case which constructor we're going to call, because that's what we're actually referring to here for that kind of constructor method. So it'll be exactly the one we're asking for. Then we have get field and set field, which are used when trying to get a given property. So we can either get the set or the get accessor, because if you remember in the property syntax, it looks like it's just a single method that encapsulates the get and the set, but when it compiles, you end up with separate get and set methods. So when you ask for a given property name, you need to specify which one you're looking for, the get or the set accessor. And then finally, invoke method indicates we are going to, when we invoke a given method, that is exactly what we're attempting to do. Dynamic binding is the ability to load an assembly at runtime that you might not otherwise have a reference for at design time. So when you run your program, the CLR looks for all of the assemblies that you currently have referenced, and it loads in the assembly manifests. If you do not have the assembly early bound, that process is delayed until you request that particular assembly. So if you issue, for instance, an assembly.load command and you provide it the assembly that you're looking for, it will do several things. First off, it's going to look to see if it already has that assembly in memory. If it does, it will use that one. Otherwise, it will look in your local directory. In other words, the directory where your executing assembly is located. If it can't find it there, it will then look in the global assembly cache to see if your assembly is a shared assembly. Once it finds that given assembly, then it'll load the assembly manifest, and then you'll have a reference to that assembly in your application. From there, you can create types that are in that assembly. So you can actually find a type that's in there and call a constructor using the reflection techniques in the system.runtime.reflection, or excuse me, the system.reflection namespace. Now, as you can imagine, all of this stuff which is done typically at the beginning of your runtime where it loads up the manifest, it does take a little bit of time. So the late binding techniques that we're discussing here should only be used when necessary and not when you actually have the ability to do early bound references. So early binding is definitely the way to go, and this technique is only to be used when you have no other way to get a reference to an assembly when you're designing it. Now this could be very beneficial to use if, for instance, you do not want to hard code your application against a specific version of an assembly. So you want to be able to use any particular version without having to specify that it must be version 3, for instance. So you just want to use whatever version is available locally in the assembly's directory. Another reason you might want to use this technique is in the plugin environment, where you want the ability to load external code at runtime that you don't have any knowledge about at design time. Dynamically loading an assembly in .NET is very similar to loading a Win32 DLL using the load library function. However, the biggest difference here is we have this assembly class which has load, load from, and load with partial name methods to make this process much easier. And you would use the appropriate method based on the information you know about the assembly you wish to load. Now, the standard load command is by far the best choice of these three functions because it will use the probing technique, which I mentioned previously, where it'll look in the current directory, it'll look in memory, and then it'll load from the global assembly cache. Now, load from is the one you would use if you want to specify exactly where on the hard drive you will find this given assembly. So it allows you to say, this is exactly what I'm looking for, where it's located. And this might be the appropriate way to go if you had a plugin type environment. However, this would only really benefit over the load method if the assemblies you're trying to load dynamically are not in the same directory as you're executing assembly. And then finally, load with partial name is a method you can use if you do not have all of the bits of information to load a given assembly. So you don't have information like the culture or public key token, for instance, and you just want to go off of a name. Now, the nice thing about load is that you can also do very similar techniques, but it will perform, again, using the probing techniques mentioned before. Field info and property info define basically fields or properties that are defined within a given class. So field info provides access to the metadata for a field, provides properties you can use to query information about a field, such as is public, is static, name, etc. Property info pretty much gives you the same information, except it gives property information. Field info allows you to dynamically get and set fields of a specific object instance. And field info has no public constructor, so to get field info, you have to call either get fields or get field. And the same goes with property info. There is no direct constructor you can call to build one, so you'll have to call either get property or get properties to get a given property info. In this example, I'm going to demonstrate how we can set a given property value for an instance of a class. So on the left-hand side, we have a class called person. I want you to pay close attention to the property called last name, because that is the property we are going to adjust using reflection. So on the right-hand side, we create a reference to a type of person. So we have type T equals type of person. Then we are going to retrieve the last name property info. So we use the t's get property function, and we pass it last name, and we're saying we're looking for the set accessor, public, and instance. So that defines the property we wish to retrieve. Now, if you were to leave out instance, you probably would not get a valid property info object back. In fact, it would be null. So when you are looking for a given property or a given field, given method, doesn't matter which of these get functions you call, you want to be as specific as possible so you avoid any conflicts. So once we have that PI property info object, we can then call set value on it. But notice here, we have to create a person first because we are accessing an instance member. So we'll have to create a person, and we'll assign Bill Gates to be the person's name. And then we say pi.setValue, and the first parameter is the object that we wish to set the property for. So we pass it p, which is the person we just created. Then it asks for what is the value you wish to set. In this case, we want to set the value Jones. That last parameter, which is indicated by the null value, would be for properties that have indexers. In this case, we do not have an indexer. It's a simple string property. But let's say if it was an indexer type property, we would specify at which index we wish to set the value. And then if we output that, you can see that the name changed from Bill Gates to Bill Jones. If we wanted to access or modify a static property, however, notice here where we have p as the object we're passing, we would simply change that to null. That would mean modify the static value for that given property. Since we don't have any static properties in this class, that can't be demonstrated here. Method info is going to be very similar to all of the other info type classes you get with reflection, except this method info class is going to be pointing to a specific method. So what you get is the isPublic, isStatic, name, same thing you get with property or field info. The biggest difference with method info, however, is it allows us to do something called invoke, which means we wish to execute that given method. So by creating a method info object reference to a given method, it's almost like we're creating a delegate. So methods can be invoked dynamically in a number of ways. So most members of a type can be invoked using the invokeMember method of the type class. Methods can be invoked using the invoke method of the methodInfo class. Properties, get, and set methods can be invoked using the getValue and setValue methods of the propertyInfo class. Now invokeMember is more flexible, while the other methods are more efficient. InvokeMember must bind to a particular member on every call. The other methods bind to a member once and can be invoked multiple times. So if we were to create a methodInfo object, we already have a reference to the method we wish to execute against. However, if we were to call the invokeMember of a type object, you have to provide to it the string name of the method you wish to invoke. So basically, it has to go out and call the getMethod function where you would have already done it if you have a methodInfo object. So if you're going to make repeated calls to a given method using reflection, the best approach would be to get a handle to that method using a methodInfo object and then invoke directly upon that methodInfo. In this example, we have a class called MathStuff. We have a static method called add, which will add two doubles together, and then we have an instance method called multiply, which will multiply two values together. Now the reason I did it this way is so you can see how it works when you're using a static member or an instance member, so you can get experience and more familiar with how the calls are different. So notice at the beginning of the example on the bottom, the first thing I do is I get a type reference to the MathStuff class. From there, I can call getMethod. Now, this is going to be different depending on whether or not it's a static or an instance member. So what will change is whether or not I issue the call using the bindingFlags.static or bindingFlags.instance parameter. So we want to get the static method first, so when we say t.getMethod, we say add, and then bindingFlags.public and bindingFlags.static are ORed together. Assuming the miAdd variable is not null, then we can issue the invoke command on it. And notice here, the first parameter is null. That is how you invoke upon a static method, because we have no particular instance to invoke upon. Then I have to provide the parameters I wish to invoke with. In this case, I basically compact them or compile them into a new object array. So in this case, I'm passing 6 and 9 for values v1 and v2 respectively. The sum is what comes out, and because invoke returns an object, I have to cast it to double to hold the appropriate value. And then I can output the results. Now we can also do this below by using the instance member for the multiply function, and notice the biggest difference on the getMethod call is going to be I change static to instance for the binding flags. Then I have to create an instance of the class I wish to invoke the method upon. So I create an instance of MathStuff called ms. Then when I call the mi_multiplies invoke method, I have to pass it, instead of null this time, I have to pass it that object reference ms. And then again I pass the new object array 6 and 9. And I get the result, again cast it to double, and then I output the result. Now there are by far easier ways to deal with this type of reflection as of .NET 4.0, because we have the new dynamic keyword in the dynamic language runtime, but that'll be demonstrated later on. The reflection API allows objects to be created dynamically by name without first adding a reference to the library that contains that class. This process is sometimes known as late binding. So we have system.activator.createInstance, which has many overloads to accommodate various activation semantics. And then we have the assemblies.createInstance method, which also will create dynamic instances as well, but it's a different set of parameters. Typically speaking, if you have a reference to the assembly you wish to create an object on, the assembly.createInstance of basically it's a constructor call, is going to be by far the more efficient one, because system.activator.createInstance typically requires it to go search for that assembly first before you can actually create the instance. Now, as I mentioned previously, the DLR, the Dynamic Language Runtime, provides something known as the dynamic keyword, which is probably the preferable way to hold references to dynamically created objects. And the reason is because dynamic allows us to use the method names natively. Say we have an add method, we would be able to call that method without doing a formal method info.invoke. Because the dynamic keyword allows you to say whatever your object name is, dot that method before compile time, even though at compile time it doesn't know what that method is. So at runtime, it will evaluate the object and evaluate it for the methods you are trying to invoke. Here's an example of how you can use the dynamic keyword to dynamically create an object. So notice here we have assembly A equals assembly.load testlib. So we're making an assumption we have the ability to find the testlib DLL, which is defined at the bottom. As you can see here, it's a simple library that has a class called student, which has 3 properties: date of birth, first name and last name, a constructor that accepts 3 parameters, and then a toString member. So when I create this student using the dynamic keyword as opposed to, for instance, object, it allows me to make calls such as setting the last name. But first, let's take a look at how you use the createInstance call. So the first parameter is going to be the fully qualified name of the class we are trying to create an instance for. The second parameter indicates whether or not we should ignore the casing of the characters. In this case, testlib.student. I know the spelling, so I can say false. Then we have the binding flags.createInstance binding flag to say we are looking for a given constructor. The next parameter, which is a null, corresponds to a custom binder you can create, which will deal with the coercion of arguments to their correct types, etc. In this case, I'm going to use the default binder, hence null, which will take the values in the object array and just pass them one for one and do the default conversions from what is given in the object array to their correct parameters in the constructor. Then I specify the culture that I wish to use for creating the instance, and this really would only apply if we had several libraries where they had different cultures each, but we are using a neutral culture typically, so we can just use whatever the current culture of our running application is. And then finally, we have that last null, which is going to indicate special attributes for calling the constructor. Again, we don't want to do anything special here, so we can leave that null. So yes, that is a long-winded way of creating an instance of an object, but this is what you have to do using reflection, so you can actually find the particular constructor we're looking for and make sure it calls the correct one, sending the appropriate values, etc. Once it's created, now I can output the value by saying console.writeLine student, and because console.writeLine immediately looks for the toString method if you don't supply a string parameter or some other data type it recognizes, it will call the toString method, as you can see on the top right, and in fact uses the format I have defined in that toString method. And then I can say student.lastname equals Yates. This is where the dynamic keyword really comes in handy. Because if we used object instead of dynamic, we could not say that student.lastname because last name is not a member of object. With dynamic, however, it assumes you know what you're talking about, and it'll wait till runtime to try to find that property called last name. Yes, if last name did not exist, you will encounter a runtime exception. However, if you're careful and you are sure about your naming conventions, then this shouldn't pose any serious problems. It does make it much easier than having to create method info objects and doing the invokes and all of the other techniques you would have to normally use when reflection comes into play. So definitely the dynamic language runtime, the DLR, really enhances your ability to use reflection effectively. On this page, I'm demonstrating a technique I use daily in production. I created a code snippet that automatically puts in the code you see below anytime I type in the letters try CF. Try CF is something I came up with, which will create the try block and then put the catch block you see, and then leave a comment between the two curly braces of try. That's where you're going to put your code. So in the catch handler, notice what happens. I create a method base object, which is going to use reflection, and it's going to get information about the current method being executed. With that MB variable, I can do a bunch of neat things. In this case, I'm going to write out to the debug window, and I'm also going to write out to the event log information about what the exception is. So notice here when I do the debug write line on the diagnostics namespace, I get the declaring type.namespace, declaring type.name, and then the name of the current method. So that gives me the fully qualified name of this method, namespace.class.method, without actually having to hard code it in the string. So this is something that can be used with any method. And then I pretty much do the same thing. Instead of writing to the debug window, I write to the event log.